Welcome to Brain Vision.
In this example, we're going to be determining the electric field at all points in space for the following configuration. Okay, what we have is a conducting spherical shell with a point charge Q at its center. So here's Q at the center, and then that's surrounded by a conducting spherical shell. Okay, it's got inner radius A, outer radius B. Okay, this is supposed to be a circle, but you can see that it's not quite a circle, but we're going to pretend it's perfectly spherical, okay? The shell has a charge on it as well, and this charge is going to be equal to negative 3Q. Okay, this charge in the center has charge Q. So I want to find the electric field in three regions. I want to find it for R less than A. Okay, R in between A and B, so less than B but greater than A. And then I want to find it for R is greater than A. Okay, so first we're going to be looking at the region inside the hollow spherical shell, but outside of that charge Q in the center. So this will be my first region. Then our second region is from A to B, so we're inside the shell. And then my third region, this is region 2, my third region is everything outside of the shell. Okay, so let's start calculating these fields. We're going to be using Gauss's law for all three locations. Okay, Gauss's law says that the E dot dA equals Q enclosed over epsilon naught. Okay, so for my first region, when we're inside this hollow spherical shell, my Q enclosed is just Q. My surface integral, that's just E is perpendicular to the surface everywhere because we have that spherical symmetry, so we can use Gauss's law. So E dot dA is just E times the surface of the sphere, 4 pi r squared. Okay, so E for R less than A equals Q over 4 pi epsilon naught r squared. Okay, now we want to look at region 2. That's between the two walls of the shell. Okay, the shell is a conducting shell. What do we know about conductors? We know that there's no electric field within them. Okay, all of the charge resides on the surface. Okay, the two surfaces, so we have a positive charge in the center, so we're going to have negative charge distributed on the inner surface of the shell. We'll have positive distributed on the outside. Okay, so for region 2, E equals 0. Then for region 3, now we're outside of the shell. Okay, so again, we can use Gauss's law here. Okay, now we have some enclosed charge. What's my enclosed charge? Okay, my enclosed charge is Q, the charge in the center, plus the charge on the shell. We said the charge on the shell is negative 3Q, so my Q enclosed is negative 2Q. Okay, my E dot dA, we still have the spherical symmetry, so that's just E times that surface area. Okay, so E for R greater than B, and I should write here for R less than B greater than A. Okay, so for R greater than B, my electric field equals negative 2Q, that's my enclosed charge, divided by the area of our Gaussian surface, R squared times epsilon naught. Okay, so let me move this actually up here because we're going to need a little bit more room than I was anticipating. Okay, so I'll put this one next to here. E for r greater than b equals negative 2q 4 pi epsilon naught r squared. Okay, so now what we want to do is find the surface charge density on the inner and outer surfaces of our shell. Okay, so let's see. We have Q, positive Q here. We know the charge that's going to be distributed over my inner shell is going to be negative Q. Okay, so my surface charge density on the inner, so we'll call this, this was for region 3. We'll call this whole thing, this was all part A. Let's move on to part B. Okay, so the charge density on the inner sphere or the inner wall of the shell is just the total charge, so negative Q divided by the area of the shell, so 4 pi b squared. Nope, the inner shell was the A shell. Okay, so 4 pi A squared. Okay, so this is for inner. Then my surface charge density for the outer shell is, we have a total charge of negative 3q on the shell, so negative 1 is here, so that's going to be negative 2 on the outside of this, on the outer wall of the conducting shell. So we have, that's going to be equal to negative 2q over 4 pi. Now we use b squared. Okay, so those are our charge densities. Now the problem wants us to sketch the electric field lines. Okay, so let's put Q, I had that as green. We have Q here. We have the shell out here. Okay, so let's look at our field lines. We have a positive charge in the middle, goes to the outer shell. 2, 3, 4, 5, 6, 7, 8. Okay, so I'll give that 8 field lines. Okay, note that they're symmetrically spaced. They all have the same magnitude. They'll all be perpendicular to the surface of both the charge and the shell. Okay, and then we have on the outside of the shell, we have 2q, so we're going to have twice as many lines, and they're coming in 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So those are my field lines. And then the last thing we want to do is draw a graph of the electric field versus distance. So we have R, E. Okay, at the origin, obviously we know that's the singularity, so it comes in here. Let's label A and B. Okay, decreasing as we approach A, where it swiftly drops to 0. Okay, at B, picks up at B and continues to decrease, approaching 0 as R approaches infinity.